Mm. Hello, welcome to the second part of the video on chapter 1. So, we move on to equations of equilibrium. So, this is very important. Equations of equilibrium, we are inching towards more towards analysis calculation. So, this is the starting part of the analysis. So, structure or one of its members is in equilibrium when it maintains a balance of force and moment. So, when it is static, it's not moving. So, it is in equilibrium. So when it is in equilibrium, it maintains the balance 0 0 force and moment. So for equilibrium, summation, the total force acting on the horizontal x is 0, vertical or y is considered 0, and the z, if it is analyzed in three axis, y x, maybe this is z. So 0, it doesn't move. And also the moment, the force here, this is force F, and then moment is also 0, x, y, z. So in the axis of x, y. So basically 0. Most structure can be reduced to only two axes, x and y. Um, and then determinacy. Determinacy, what is determinacy? Determinacy is equilibrium equations provide both the necessary and sufficient conditions for equilibrium, and all forces can be determined strictly from this equation. So you can determine all forces, y, z, x, moment, a number of, but to determine you need to analyze the type of structure. So that is determinacy. A number of unknown forces, unknown, you don't know, basically when you have a frame. So unknown is basically the reaction and support. So number of unknown forces is greater than equilibrium equation. For example, in this we have these three, fx, fy, and moment at naught. So the number of equilibrium we have 3. Number of unknown forces we have here also 3. So equal. If it is equal, so it is statically determinate. But in the case when you find it uh, too many forces, too many unknown forces, for example in this one, pin here, so you have too many unknown forces here. You have at least 5 unknown forces. You have 5 unknown forces, but you still have 3 equilibrium equations. So that the structure is statically indeterminate. You cannot solve the equation. You cannot solve the structure, analyze the structure, and solve for the unknown forces using this statically indeterminate analysis. So first, when you are dealing with any problems, so you need to determine the determinacy degree of determinacy. So if it is equal, so it is determinate. The unknown forces, the equations to solve, uh, so so R stands for the unknown forces. This is unknown forces. This is the unknown forces. And then N is the number of members. So you have, if you have a frame connected by 2 members, so you have 2 members of structures. The R is the reaction here that you have according to type of support. So if it is a number of unknown forces, unknown reactions is equal to 3 times the number of member. So it will be statically determinate. If it is number of reaction unknown forces is too big against 3 times of members, it will be statically indeterminate. So Number of members helps in analyzing the statically determinate static in structure. This is for information. The additional equations needed to solve for the unknown equations are obtained as compatibility equations. Okay, let's take a look at example 2.4. Classify each of the beams as statically determinate or statically indeterminate. If statically determinate, report the number of degrees of indeterminacy. The beams are subjected to external loadings that are assumed to be known and can act anywhere on the beam. So you're dealing with this structure. In analyzing the determinacy and stability, you don't need to know the where are the load acting. You just need to know the unknown forces, which is the reaction forces are unknown forces. So for example, here you have 1, 2, then 3, because this is roller, this is pin. So you have 3 unknown here, 3 unknown reaction, and then you have 1 member only. So this is 1 member bar. So 3 is equal to 3, so it is statically determinate. Next, also 1 member, so you have 1 n, but you have 5, 1, 2, which is moment, 3, x, and then this is number 4, this is number 5. So you have 5 unknown forces, so it's too big, 5 against 3, so it is statically indeterminate to second degree. How we get second degree is 5 minus 3. So you're lacking 2 more equations. You have another 2 equations, so you can solve this this structure. Be what may, doesn't matter where you put the load. As long as this is satisfied, we can solve the equation. Next, example 2.4, you have 2 members, 1 and 2, and then you have a reaction here. Your reaction is 1, 2, 3, 4, 5, 6. Oh no, your this is similar to be counted. So you have 1, 2, 3. This is counted as 1 because this is similar. 4, 5. This is similar. This is similar. 6. So you have 6. But you have 2 members. So 6 is equal to 6. Unknown forces is 6. 3 times 2 members is 6. So you get statically determinate. Okay, next example. Your reaction is 10. Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9 moment, and 10 x forces. So you have 10, but you have members 3. 1, 2, 3. 3 members. So 10 more than 9. This is 9. So it is statically indeterminate to the first degree. Okay, example 2.5. We have 2 members. We have 7 unknown. 1, 2, 3, 4, 5, 6, 7. This does not count as similar. So this is statically indeterminate to the first degree. 7 minus 6 equal to 1. Next is a frame. You have 3 members. 1, 2, 3. You have reaction 2 reaction here. 1, 2, 3, 4. Because it's also pin. 5, 6, 7, 8, 9. You have moment here because it's a fixed support. So 9 equal 9. This is statically determinate. Okay. So you can do this example by yourself. to help sharpen. Uh, this is definitely will be in your final. So next is stability. What is stability? To ensure equilibrium of structure or its members, which means it's stable. So if this structure is here, you have pin here and then roller here, so you know the structure won't move, won't crumble, it will stay static. So that is stability being supported. Must satisfy equation of equilibrium, and then um, satisfy equation, and the members must be properly held or constrained by the supports. Shown here, you have roller here and then pin here. Partial constraint, fewer reactive forces than equations of equilibrium. So summation of fx is equal to 0 will not be satisfied. Example here, you have a pin here, a fix here. As you can see in the structure here, this support is actually a roller support, a bit of a roller, because it only restricts movement in moment and also vertical forces, as you can see here. So the support allows movement in the horizontal or fx. So the fx is equal to 0 will not be satisfied, because in this case the frame here can move, it's not static. So if it is considered partial constraint and it's not stable, so you cannot analyze unstable structure, because it is dynamic, it can move. Next is improper constraint. So the previous one is partial constraint. You constrain but partially. In one of the axes is not constrained, and the structure can still move. In improper constraints, uh, in some cases, unknown forces may equal equations of equilibrium in number. However, instability or movement of structure could still occur if support reactions are concurrent at the point. So in this example, you have roller, both roller, and B also a roller. So when, if you imagine, when you apply this load here, so the bar here can move. I mean, logically, A will move downward and C will move upward. So it does not satisfy the structure cannot be considered as static. Can move when you apply load here, unless it is being pinned here or fixed here. Improper constraint also when PD is not equal to 0. Rotation about O will take place. For example, similar instability can occur in all reactive forces are parallel. So rotation, this is talking about rotation about 0 is talking about this one. So basically when A move downward, A move outwards, so there will be a rotation here. So it's not static. Similar instability can occur if all reactive forces are parallel. So you have this parallel support here, shown here. These are all parallel. So it is also unstable because you don't have any reaction restricting movement on the perpendicular axis or fx here. So when you apply load here, your bar can move here unless you're analyzing for dynamic analysis. Example 2.7, 2.7. Classify either it's stable or unstable, such as subjected to arbitrary external loads that assume to be known. So we have this one here. So you have pin here and roller here. So you have perpendicular support. So there is no issue on this. And then the constraint is proper, pin here and roller, so you can solve this equation because the structure is stable, statically determined. In this one, um, this one is considered unstable. This one is considered unstable because you have roller here, and then when you apply load, the roller will go here, so there will be movement about B, so there will be rotation if you put any load. So the structure is not properly constrained unless it is a pin here and roller here. As you can see here, also the forces reaction is parallel. If you combine this Fy and Fx, it will be parallel to this roller support. So it is similar to this issue when you have the forces acting parallel. So when it's parallel, so it becomes unstable. Okay, next example, a beam, pin. So as you can see here, it's parallel, so it is unstable. This one, why it becomes unstable? Because the forces is also parallel, and then the movement here is not properly constrained. So when the Fy here, Fx is not equal to 0 because there is no constraint here. So there will be a movement towards here. There will be it will not static the structure. And then application, the last one, last topic on this chapter, application of equation of equilibrium. So consider three-member frame subjected to loads P1, P2. So this three-member frame, 1, 2, 3. So there are 9 unknowns in total. 9 unknowns. This is unknown. Okay. Unknowns. 9 equations of equilibrium can be written for each of the member. Because R equal to 3n. We have 3 members and then 9 reactions. So we will satisfy. So it will be statically determinate. So you can determine the structure. So if there is a value here, there's value here, so you can actually calculate the value at the reactions. Example number 2.8, determine the reactions of the beam as shown. So this one has a real value. So you have pin here, and then a roller here, and a force acting at an angle. So basically this R equal to 3n, your n is 1, and your reaction is 1, 2, 3 only. So it is statically determinate. Is equal to 3. So first you write your equation of equilibrium. Let's say you start with fx. So summation of fx towards the right is considered positive. So ax is positive. Ax is positive. Ax minus 270 cos 60. 270 cos 60. So 270x is here. 270 cos 60 is negative. So minus 270 cos 60 is equal to 0. This is your equilibrium equation. So your AX is 135. Next is moment equation. With anti-clockwise moments in positive direction, summation of MA, moment at A, moment here. So moment here, summation of moment here. So when you're considering here, so from this point towards here is considered the moment arm. Moment arm. So you have by moment arm is 3 plus 1.2, which is 4.2. And then this one here, you have moment of 270 sin theta times 3 meter, which is the moment arm, and then the last one you have a moment of 67.5 kilometer meter. So that doesn't have any moment arm. So you write all of this equation with consideration that anti-clockwise, this is anti-clockwise, is considered as positive. So this one is clockwise, is negative. This one is anti-clockwise, is positive. This one is clockwise, which is negative. So you can see here, um, in this equation, also consider the thickness of the beam. We usually don't consider this, but it can be considered. So you have a moment here, 270 cos 60 times the thickness, half thickness of the beam, which is 0.3. So this one is anti-clockwise, so it is positive. So as you can see here, you write positive cos 60, negative sin 60. Then by is positive because of this counterclockwise, anti-clockwise, and then the moment at the end of the bar is negative because it is clockwise. So solve this equation, you will get your by is equal to 173.4 kilonewton. So you solve your by, you solve your ax, and then you can solve your ay because you solve your by. So in the y-axis equation of equilibrium, you have this one 270 sin theta, negative because downward consider negative, upward consider positive. So you have by positive, and then you have ay positive. So there you have it, negative, positive, positive. You solve for ay, so you get your ay 60.4 kilonewton. So this will be used throughout the entire course, starting of analysis. I think um, you've learned about this in fundamental of solid mechanics. So this is just a continuation. So next is example 211. We have ABC fixed at A. So this is fixed. This is pin at B, and then C is a roller. So you have two members, n equal to 2. Unknown, you have 1, 2, 3, 4, 5, 6. Now you have 6. So 6 equals to 3 times 2. 3 times 2, so it is statically determinate. So resolve according to members. So you have pin at B, so you don't have any moment here, and no moment. So this is your free body diagram. So you have MA, AX, AY, BX, BY, and then CY rolling. So maybe you can start by BC. This is a solution. You start at moment at C, negative 8, negative because it is clockwise, positive BY. So BC you have 8 clockwise, BY times C is anti-clockwise, so positive, so you get your BY 178. And then so for FY you get your CY, which is 1.78 also, because you already know BY, then you can get your CY. Then so for FX, so your BX is equal to 0, so easy, and remove this from equation. And then you move on to segment AB, next member. So moment at A, we take moment at A, because this is a fixed support, so you have your reaction moment here, MA. We assume to be positive, anti-clockwise, easier. So MA is positive, and then it's 36 times 3, which is the external load with moment arms of 3 meter. and 3 6 times 3 because it is clockwise, it's negative. And then this is by 178. So b1 is 178 times 6 meter moment arm length. So you solve for this equation, you get your MA at 7.3 kilonewton meter. And then you solve for FY is positive, taken as positive, and then this is the external load 36 acting downwards, and then by acting upwards. This is by acting upwards, and then you will get your AY as 4.2 kilonewton, and then FY is also 0 because BX is also 0. One thing just to remind you that when you are doing this frame, you are solving, analyzing the frame, make sure that um, for this example, we assume the Vy is acting negative, acting downwards. We assume. Usually we assume it's positive, but in this case, if you are you're looking at structure like this, so logically By will be downwards because you want to um, counter the value of Cy. So based on your assumption, if the assumption is right, for example, this it assume the solution assume that it is acting downward. So the free body diagram remains the same downward. But in case if you're having negative uh, a wrong assumption, like you assume positive and then you get the value of by is negative, right? So make sure that you make corrections to your free body diagram, because um, when you are dealing with two members, the force acting at the joint will be in the opposite direction. As in this example, when the solution solve that by is acting downwards, so by on the other member will be acting in the opposite direction. So you cannot draw by here in downward direction, because it won't satisfy each other. It won't be in equilibrium. So because if you make that mistake, it will affect your solution in other parts, in the next part, because you also make wrong value, wrong directions of AY. In this case, if you wrongly assume BY. So it's a bit tricky on that side lah, on that side. The rule is once you solve, then draw again your free body diagram to be on the safe side, and then on the next free body diagram, make sure to draw the opposite direction. As you can see, a by and then bx also in the opposite direction, so you'll be in equilibrium. Okay, so next we will take a look at this example 230. So for now, see you on the next video.